Hello everyone, welcome to this online course of material characterization organized by NPTEL. I hope you all have gone through these video lectures of optical microscopy and its applications and laboratory demonstration and so on. And what I wanted to do in this class is to have some kind of tutorial sessions where I would like to introduce the applications of optical microscopy. As you see in these video lectures, I have just demonstrated variety of applications. Optical microscopy has got tremendous amount of applications in almost every field where we use materials, structures or microstructures, topology and so on. But then when my tutorial sessions will be more with relevant to material science and metallurgical engineering and so on. But then some of these applications are more general, which can be used to in the field of medicals as well as biological materials and so on. So in this class I just want to introduce a technique called quantitative microscopy. You see, optical microscope is just used not only just to observe the topological features of materials or biological systems or any other context, but then it has got tremendous capability to obtain a quantitative informations. In fact, the quantitative microscopy itself a separate science in itself. I will not get into the elaborate procedures of quantitative microscopy or metallography, which is out of the scope of this course. But then if you want to appreciate the effective application of optical microscopy, I think you need to understand the basic idea of quantitative microscopy. I will just introduce here, I am not getting into details, but I will just introduce the basic concepts which is there in a quantitative microscopy. So what I will do is, I will just demonstrate the basic idea behind this. So, what I have written here is when we talk about a quantitative microscopy, we can divide them into two measures. One is a simple direct measure of a property or a feature on a material, which could be an optical properties of crystals or angles between the crystal faces or grain boundaries, or surface topology or topography, or you can see a case thickness on a surface coatings, or even if you look at the metallurgical phenomenon, a case hardening treatment and so on. So, this is a direct measure. The other one is to deduce and quantify three-dimensional structures of materials. So, this is the second measure in a quantitative microscopy. So, how are these things are visualized? Let us see. For example, so what are all coming into three-dimensional structures of materials, such as grain size or particle size. You have volume fraction of constituent in a two-phase materials. It could be a particle fraction or a independent phase of a multi-phase or polycrystalline material. They can be deduced and can be quantified in the microstructures. They are all three-dimensional structural parameters. So, these are the two broad category under which one can use quantitative microscopy. So, what are the mathematical relationship to obtain quantitative measurements? Briefly, I am going to just tell one by one. First, we will take it up measurement of volume fraction. So, what I have written here is, it is mathematically estimated that in a material in which the constituents are randomly distributed, the volume fraction of the constituent, that is VV, is related to the measurements on a random 2D plane through the material by the following equation. That is, VV is equal to VC divided by VT, which is equivalent to AC by AT, LC by LT, which is again equivalent to PC by PT. So, what are all these things? We will just describe one by one. See, the VV is the volume fraction. So, VC volume of constituent, VT is total volume of material, so VC divided by T is the volume fraction. So, you have the volume of the constituent divided by the total volume of the material. Similarly, you have area of constituent, total area. So, similarly, you have AC by AT, that means you have area of the constituent divided by AT will give you the area fraction, and then you have two more, that is so what you are now seeing here is, so the volume fraction of a constituent in a two-phase material or a multi-phase material or a second phase particle fraction in a matrix can be related to areal fraction or areal analysis or a linear analysis or point count method. So, this is a fraction of a line fraction or intercept fraction. This is a point fraction. So, point fraction, line fraction, area fraction is equal to volume fraction. So, it is very powerful expression to get some numbers out of from the topological microstructures or material features. So, we will now briefly introduce or briefly mention how to carry out these things in actual terms. So, what I will now do is I will write few lines about what is areal analysis, what is linear analysis, and what is point counting, and how you can carry out this exercise in a using optical micrographs or even scanning electron micrographs and so on. But then let me first define what are these technique means. So, what I have written here, areal analysis means measuring the areas of the grains of a constituent or the particles, whatever we are interested in a two-phase or multi-phase material in a number of photomicrographs. So, please make a mention here, this is, you cannot do this on a single photomicrographs, it is a number of photomicrographs. The more number of micrographs we make a measurement, the more the accuracy will be, or in other words, the more number of photomicrographs you involve, it will be a more representative of your material rather than it will have a biased result. So, for this is applicable to all the techniques which I am going to mention. So, the number of micrographs you measure or make measurements, you have to maximize the count or a measure in order to get an appropriate representation of the material or more accurate values. The second thing is linear analysis. So, what you do in linear analysis, a random lines say at angles of approximately 15 degree to each other are superimposed on the microstructure, and the length of the intercepts through the each of the constituents are measured. So, you have the LT is summation of L alpha, L beta, etc. up to L infinity, where L alpha, L beta are the intercepts length of the constituents alpha, beta, etc. So, no matter how many constituents you have, these expressions are valid in this fashion. So, this is a brief definition of linear analysis. Let us move on to the next one. So, here in point counting, we superimpose a grid on the image of the structure and count the number of intersections, that is points falling within the desired constituent, that is PC, and compare it with the total number of intersection PT. So, that is what we require, these two quantities we require to find out the fraction. So, this is how it is done, point counting. So, with this relation, you can also find something called weight fractions. When you have this relation, we can also find weight fraction, that is W, which are useful. That is so we have the WW, that is a weight fractions. This is VV into rho C divided by rho M, where rho is the densities of the constituent and the matrix. So, we can also find the weight fractions. if you have the data with you. So, what I have just gave a definition of what is the method of measuring the volume fraction of a constituent in a two-phase or a multi-phase material. I just repeat, we can do it in three methods. One is areal analysis, secondly lineal analysis, and third it is a point counting. Okay. So, this is the first technique on the quantitative microscopy. The next one is we will just look at some of the procedures or definitions of finding out the grain size. See, the next one is grain size and grain surface area. What I am just going to say, this is a very simplest way of looking at the grain size, but there are more rigorous way of measuring the grain size. Mathematically we can do it, which also I am going to show you, but this is the most popular in the industrial practice, where the grain size is designated by ASTM, American Standard of Testing Materials, grain size number N, capital N of the standard that is closest in grain size to this specimen. So, you have the standard charts available readily for reference to compare your specimen and the grain size available on the chart. and where the capital N is defined by the equation a small n is equal to 2 to the power n minus 1, okay, where n is number of grains per square inch of an image when viewed at a magnification of 100 times. So, this is very important, because once you change the magnification, then these things will not be valid. So, we can correct that expression also when we look at some of the other examples, but this is how the basic definition is given to start with. So, a small n and there is a capital N, only capital N is called ASTM grain size number, small n is number of grains per square inch of an image when you look at the 100 times the magnification. So, I will also write So, what I have written here is, I said this is a very basic way of looking at the grain size, and you have little more better accurate methods where if you use the number of grain boundary intercepted P, that is if you count the number of intercepts, which is P, which is equivalent to the number of grains, and approximately when you use this random lines. Of course, all these techniques you have to consider using the random lines, and that L is equal to total length of lines and total number of intercepts, which is equal to 1 by Pm, where P is the number of grain boundaries intercepted and M is the magnification, which is nothing but inverse of number of intercepts per unit length. So, this is a relation again, you can see that, where L is the number of intersections per unit length, L is the length of the test line, M is the magnification. Suppose if you measure the L, capital L like this, and which is related to the equivalent grain size number G. So, we were talking about earlier ASTM grain size number capital N. Now, we call now equivalent grain size number in another estimate of grain size capital G, which is related to L by this expression, that is capital G is equal to minus 10 minus 6.64 log base to 10 L. So, this is another empirical relations by which you can measure the grain size with little more accurate by the equivalent grain size number G as compared to N. So, I will also show some more rigorous method of measuring grain size or a particle size. I think I will also show some of these techniques, how it is being used in a practice, some of the worked out examples I am going to work out in 1 or 2 problems in each category, so that you will appreciate what we are talking about. So, what I suggest is now, before going into the next level of rigorous calculations of grain size, I would like to show some of the applications of this itself. Or first let me show you what I mean by this grain size, ASTM grain size number. For example, if you look at this slide, you have the 3 different micrographs A, B, C, and if you want, this is a polycrystalline material of, the exact material name is low carbon steel, and you have the several nominal ASTM grain sizes are shown here. For example, the image A belong to grain size number ASTM grain size number 7, and B is number 8 and C is number 9. So, they are all etched microstructure at the magnification of 100 times. So, what I want you to just appreciate is, as the grain size number increases, okay, the physical size of the grain size, it is becoming smaller. So, this we have to appreciate. So, as the higher the ASTM grain size number means you have the smaller grains, okay. So, that is the one thing you have to keep in mind, and I will just show you in the next class with few numerical examples how we can calculate the ASTM grain size number from an optical micrographs, or some of these measurements are typically done even using a scanning electron micrographs, and these are all readily available in some of the industrial shop floors, where you can readily look at the grain size for a quick reference. it may not be a very accurate calculations, but for a quick reference you will have this in the industrial practice. We will see it in the next class. Thank you.